Welcome to Share Science. Over the last few weeks, we've been nerding out on the power of magnets. If you haven't already seen them, you should go back and watch the first video in the series, which we've linked in the top corner. Today, we're closing out the series by looking at possibly the most futuristic technology yet: levitating trains. Maglev technology has been around for several decades and is starting to hit its stride in countries like Japan, China, and soon the United States. A big component of how these systems work is superconducting magnets. So if you haven't already seen it, you should go back and watch our previous video on how superconductors work as a primer. All caught up? Okay, let's hop aboard and find out how. At its core, maglev technology relies on the fundamental principles of magnetism. To comprehend how maglev trains operate, it's essential to understand the basic magnetic forces that shape their movement. Magnets possess two poles, a north pole and a south pole, and these poles can either attract or repel each other. This principle becomes the foundation of maglev trains. Imagine a typical magnet, like the one found on your refrigerator. When you bring the north pole of one magnet close to the south pole of another, they attract each other, pulling together. On the contrary, if you try to bring two north poles or two south poles close, they resist each other, creating a repelling force. Maglev trains exploit this repelling force to achieve both propulsion and levitation. In the case of maglev trains, the vehicle itself contains powerful magnets with alternating poles, and the tracks underneath also have a similar arrangement. If you try to imagine what these electromagnets inside the train look like, you might imagine something that looks like the electric motors we covered a few weeks back. But those designs have their limits, as increasing current in these designs creates lots of heat and uses a lot of energy. In the case of the most popular maglev designs, the magnets used are actually superconducting, which means they can generate huge magnetic fields with no losses. Current superconductor technology has to keep these magnets really cold, which requires some advanced liquid helium technology at a frigid 9 Kelvin, which is an astounding 440 degrees below zero, through the use of some advanced helium refrigeration technology. An additional liquid nitrogen jacket is added for more insurance at a relatively balmy 320 degrees below zero. 4 of these alternating superconducting magnets in series creates the train's power unit. Once those superconducting magnets are fired up, we can turn our attention to how we get things levitating, which involves more electromagnets embedded in the track. These magnets are actually coils of wire in the shape of a figure 8, which creates opposite magnetic poles when current is run through the wire. An opposing pole is made in the bottom loop, which repels the magnet in the train, and because the same thing is happening with magnets on the other side, the train has nowhere to go but up. Now that we understand how the train can float, let's look at the propulsion system that can move the train at speeds upwards of hundreds of miles an hour. The propulsion system also uses magnets, but these electromagnets are driven by a series of alternating currents that interact with the same superconducting magnets in the train to pull them along. As the visual shows, as soon as the attracting poles approach one another, the frequency is switched, and that magnet is made to repel while its neighbor attracts. Cool, right? By adjusting the frequency of the electromagnetic switching, the system can control the train's speed, upward of 300 miles per hour. Okay, so if the lack of friction is such a game changer, why don't we see more of these maglev trains? Well, like a lot of things, it comes down to cost. This graph shows the amount of money it costs to build and operate a single mile of maglev train, which is $200 million. Now compare that to a standard high-speed rail train that uses conventional technology like engines and wheels, but with a high degree of precision and efficiency, which costs only $82 million per mile and can travel at speeds up to 200 miles per hour. Furthermore, we can expand the comparison to traditional train travel at speeds around 60 to 100 miles per hour, which costs a meager $3 million per mile. That means the expensive maglev technology is going to be reserved for rare situations where travel time has to be limited in congested areas. High-speed rail can typically be found connecting major cities, and traditional train technology will be used everywhere else. In summary, while maglev technology represents an amazing step change in the way we travel through the power of magnets, the sheer cost of implementation with the current limitations of sub-zero temperature superconductors means they will remain rare, although plans are currently underway to create the Northeast Maglev train connecting Washington, D.C. to New York City in under an hour, which is set to be complete by 2030. We hope you liked today's video. If you haven't already seen them, you should go back and watch our previous installments that covered where magnetism comes from, how it's used in electric motors and MRIs, as well as the magic properties of superconductors and the researchers all over the world working on finding a material with these properties at room temperature. If you like this video, hit subscribe below, and you can get new content just like this every week in your feed automatically.